Welcome to this section. We're just going to look at some definitions applied to different explosions, some definitions. Now there's two that you need to know really about, and these are detonation and deflagration. Let's go for deflagration first. What does deflagration mean? It means to burn down. That's the definition, to burn down. Now, deflagration is subsonic combustion. In other words, subsonic, it is slower than the speed of sound. And the principal heat transfer mechanism, in other words, how it propagates, is through thermal conductivity. What happens is the hot burning layer heats the next layer and ignites it. So it's through thermal conductivity of the individual layers. So it keeps travelling through the material and it then ignites it. Now, most fires found in daily life, from flames to explosions, are generally, technically, deflagration. That's what most fires are, it's deflagration. Now, if it's contained, you will get a pressure wave. So it's got to be generally contained in deflagration to get a pressure wave. And typical materials that deflagrate are generally, you've got methane, propane, butane, you know, the hydrocarbons. So that's deflagration. What about detonation? Now, detonation is a process of combustion in which a supersonic shockwave is propagated. So it's not subsonic, it's faster than the speed of sound. Is propagated through a fluid due to an energy release in a reaction zone. Now, detonations are generally much more powerful than deflagration, and it's got a different heat transfer mechanism. In a detonation, the shock compression causes the material, basically it's not through thermal conductivity, it's through shock compression. What happens is, it's so fast that the different layers, its shock compression increases the temperature to the point of ignition. It's like basically a diesel engine, shock compression. The ignited material burns behind the shock and releases energy that supports the next one, and it keeps going. So shock compression is the main heat transfer with detonation. Now, because detonations generally give higher pressures, they are usually much more destructive than deflagrations. Detonations can generally be produced by explosives, reactive gases mixtures. Certain dust can give it, and aerosols. Because they're very fine, they can cause detonations. Now, the probability of detonation rather than deflagration depends on the type of gas or what have you, type of fuel. Hydrogen and acetylene, you're more likely to get a detonation than a deflagration, and they're generally LPG. The next area I'm going to cover is vapour cloud explosions. Now, you've got two types. You've got a confined vapour cloud explosion and an unconfined vapour cloud explosion. A confined vapour cloud explosion. Now, if a flammable vapour is ignited in a container, the pressure can build up and it can rupture. This is a confined vapour cloud explosion. Now, this can cause massive damage. It can cause localised damage, broken windows, etc. And it may affect nearby plant and cause more confined vapour cloud explosions. Now, fatalities have occurred during hot work on inadequately cleaned or purged 45-gallon drums containing basically flammable residues, or in natural gas or LPG explosions. Now, an example of a confined vapour cloud explosion is Abisted, 1984. Now, a methane gas in underground pumping station had been accumulating, and it caused 16 deaths and 26 injuries. What had happened was, water had not been pumped for 17 days in this underground station, and methane, which normally had accumulated, had been allowed to accumulate for all these 17 days, and it had got above its LEL, in other words, the lower explosive limit. Now, this had happened due to the temperature changes and vapour pressure had accumulated. They came in after 17 days, didn't check the atmosphere, and all they did was they switched on the pumps. Bang! Major explosion. As I said, 16 people were killed and 26 injuries. So that was an example of a confined vapour cloud explosion. Methane. Now, an unconfined vapour cloud explosion is if flammable vapour is ignited in open air, It can actually cause substantial damage if large quantities are available, for example in the Flixborough. Now this is an unconfined vapour cloud explosion. So when a large amount of material, volumeter, is dispersed over a large area and it is ignited prior to dilution, in other words, if it's above its LEL, the lower explosive amount, had time to diffuse and go below the LEL, a vapour cloud explosion will occur, shock waves and thermal radiation will occur. Now, the ratio of what is available and what is released is the explosion efficiency. In other words, how efficient was that? And that's the more efficient it is, the more damage can occur. Now, these unconfined vapour cloud explosions are actually rare. They generally require large releases of flammable vapour. You're looking at generally about a minimum of 5 tonne. Now, an example of an unconfined vapour cloud explosion is Flixborough. And this happened in 1974. And this video footage I'm going to show you now will describe what happened on the Flixborough disaster.
This was the English village of Flixborough. Quiet, peaceful, a small town of 3,000 people. Most work at the Nipro Works, a gigantic chemical factory on the edge of the town. No one could have foreseen the disaster that suddenly exploded on a June morning, just as the work shifts were changing. The blast tore the plant and village apart. Firemen battled fires that raged over 20 acres. Two days of fire left 28 dead, more than 100 injured, and reduced a $100 million plant to rubble.
Now let's summarise what you've just seen, what happened at Flixborough. A vapour cloud explosion destroyed the nitrocyclohexane oxidant plant. There were 26 people killed and 36 injured, and other plant on site was damaged. The smoke rose to 6,000 feet. In fact, aircraft had to be diverted from the incident. Now, the plant was a stage of production in the nylon production, and it manufactured cyclohexanone by oxidising cyclohexane in a series of gravity-fed reactors. Now, these had bellows installed on them on short pipe runs to allow for expansion and contraction and small movements at these temperatures and pressures which were used at, which is generally about 155 degrees, and the pressure they were used at is about 8.9 bar. Now, these reactors were cooled via brine to jackets on the outside of the vessels. Now, error one. First of all, the brine system was taken off for repairs. So instead of waiting, they just thought, well, we'll put water through it. Instead, the city water was used. Now, one of the reactors based on this collapsed because the city water was supplied at much higher pressures than the brine system. It was at 9 bar pressure, so it collapsed. That's the first error. Error two. Any plant modification should have been taken seriously, no matter how simple. And all modifications should have been approved by qualified personnel. Now, a temporary pipe was constructed to basically miss out that other reactor. And they used a dog's hind length pipe, was welded in, and it was not strong enough to take these pressures and these heat and this weight. And the men who were asked to do it had practical experience, but they were not actually qualified to do this. So a 20-inch pipe at those temperatures and those pressures could not handle it. The only drawing they had was on the floor of a workshop. The material they used was not as the manufacturers recommended. However, they were not blamed for this incident. Error 3. The lack of physical bracing or support of the pipe, so they didn't give it enough bracing. The original pipe runs were a lot shorter and supported firmly so to minimise the pipe movement and allow the bellows to operate properly. So basically they put in lack of bracing. The result was the temporary pipe was allowed to twist and move laterally due to lack of bracing, and 50 tonnes of cyclohexane was released. And it travelled away from the site, 50 tonnes of it released, and it subsequently reached a flare and it went up, exploded. As again, 28 people were killed. Now, the cost of the disaster was actually put at 27 million. That's direct cost. In the end, I'm sure it was roughly about £100 million, and that was 30 years ago. So if you equate it, massive cost to the company. The cause of the accident was a failure of the pipe, and the contributory factors: the pipe was connected without check on strength and on inadequate supports. Again, like I said, the expansion joints, the bellows, were used on each end of a pipe in a dog leg without adequate supports, contrary to the recommendations of the manufacturer. And there was a large inventory of hot cyclohexane under pressure. The accident occurred during the start-up operation, and the controller was not built of adequate strength, so that was taken out when it went up straight away. The previous works engineer had left and had not been replaced. According to the Flixborough report, there was no mechanical engineer on site of sufficient qualification, status or authority to deal with the complex and novel engineering problems and to insist on necessary measures being taken. Management deficiencies, lack of experienced and qualified staff, inadequate procedures involving plant modifications, and regulations on pressure vessels that dealt mainly with steam and air did not adequately address. I mean, this was highly flammable gases, liquids, highly flammable. A process with a very large amount of hot hydrocarbons under pressure and well above its flash point, so it was well above its flash point, installed in an area that could expose many people to severe accident, was not there. So, that was Flixborough, an unconfined vapour cloud explosion. Now, that covers the mechanisms and principles of explosions. Now I'm going to cover another number of disasters due to poor management, etc. There was an incident at General Foods, Banbury, 1981. Now, cornstarch powder was ignited and exploded, and it injured 9 workers, and it caused substantial damage to the company. What happened was it was a malfunction of conveying equipment which resulted in a feed bin being overfilled. What it was, this bin was already full and it tried to fill an already filled bin. It was not capable of detecting that it was already full, so there's no equipment in there to recognise this. Carry out analysis, this is what you should have done, is to identify possible modes of failure. So what they could have done is put some sensor on the bin that obviously once it's full, it stops trying to fill it, to reduce the risk of failure and mitigate the effects. And the role of proper plant maintenance is essential.